Hello everyone, my name is Pinhan, and I'm a PhD candidate from the University of Michigan. And today I'll talk about general symbolic reasoning engine that uses the idea of under-approximation to reason about complex SQL queries. So in our work, the core problem we study is how to automatically generate an input for n queries such that their output on the generated input satisfy a given application property. So this can be instantiated to solve many different real-world tasks. Let me give you two examples. And for instance, one task is to disapprove the equivalence of two queries. In this case, we want to find an input such that the outputs of two queries are different. And this is particularly useful for rewrite validation. As modern database systems like Calcite and MySQL rely on rewriting to optimize query performance, it is critical to ensure that the rewrites are correct by checking if the rewritten query is semantically equivalent to the original one. And if they're not, we want to generate a counterexample to help the developer identify and fix the issue. And equivalence checking is also useful for automated grading. And in this case, it allows us to automatically check the user solution matches the ground truth query. And if it is wrong, provide a counterexample to illustrate the user's mistake. And another real-world task is clustering a set of queries. So here, the goal is to find an input that can divide n queries into two sets, where queries in the same set produce the same output, and queries from different sets produce different outputs. And this is especially useful for disambiguating synthesis or generic queries. For example, when a program synthesizer or a language model returns multiple queries, we can automatically group them based on their behavior and identify semantic differences to help the synthesizer further refine the solutions. So there's prior work that tries to solve some instantiations of our problem. For example, equivalence checking for two queries. So let me briefly discuss them here. So broadly, they fall into two categories. First, we have filing techniques for SQL. Tools like EvoSQL, Xdata, and DataFiller adopt this approach. These methods are cheap and can quickly produce many test cases. However, because they generate inputs by considering no or very little semantic information, they often miss the specific inputs we care about. And the other line of work uses symbolic reasoning method. For example, where equal, coset, and QEX use symbolic techniques to reason about queries. These methods are complete, meaning that, in theory, they are guaranteed to find a desired input that meets the problem's criteria, if there exists one within the given input space of interest. But this completeness comes at a cost. They are often very computationally expensive, especially for large or complex queries. So our approach also uses symbolic reasoning method, but in a very lightweight manner. So rather than reasoning about the complex semantics at once, we try to break down the challenge and consider the SQL semantics in a way that is lightweight without hindering the completeness. So in this way, we aim to combine the best of the both worlds, fast and also complete. So now, before telling you about our key idea, let's start with a brief review of how prior symbolic approaches work. So typically, this method precisely encodes all possible input output behavior of SQL queries in an SMT formula. That is, the SMT formula encodes the query semantics for all possible inputs, such that each input-output pair of the query corresponds to a satisfying assignment. However, the limitation of the approaches like this is that precisely encoding complex operators like join may lead to many possibilities. And there are exponentially many ways that the tuples from input table can be matched and joined, depending on which tuple pair satisfy the join condition. And this makes the formula very hard to solve. So here, we show one possible way that the join operator can behave, which is there's exactly one pair of tuples from two input tables satisfy the join condition and will be joined. However, precisely encoding the join operator requires us to capture all possibilities, which can be a lot and makes the solving very expensive. So this motivates our first key idea. How about we want to consider a subset of them? because a formula that encodes a subset of reachable behaviors can be faster to solve. Therefore, we propose Polygon, which is what you get when you under-approximate a circle, which rhymes with SQL. So now, let me introduce Polygon by first explaining the core idea behind our approach. So rather than tracking all possible query behaviors, which is often extremely expensive, we choose to track and encode only a subset of possible behaviors, which is an under-approximation. So by focusing on a smaller subset and reasoning about an under-approximation of query behaviors, it brings out a formula that is often very fast to solve. So now, let's walk through a very simple random example to illustrate our approach. Consider this database with two tables. We have a faculty table with two columns, ID and name. And we also have a teachers table, which shows which professor teaches which course. And given this database, our task is to write a query to find all faculty who teach the course CS101. And the output table in this case will be like this, because Alice is the only professor who teaches the course CS101. So to ground our approach in a real-world problem, let's consider an equivalence checking task with two queries. And here we have two very simple meta queries just for illustration purpose. And Q1 is the correct query. It first joins the faculty table with teachers to find which professor teaches which course. And then it further filters the result to only include the rows that the course is CS101. And finally, it outputs the name of those faculty members. On the other hand, Q2 is incorrect. It mistakenly looks for faculties who teach CS202 instead. And our goal here is to automatically generate an input that can make the two queries produce different outputs. And now, mapping the two queries onto their abstract syntax trees, we can see that Q1 first performs an inner join and then projects the faculty names. And Q2 follows the same structures with a join followed by a projection. So now, I was talking about the concept of under-approximation for SQL. So how do we actually represent that, and what does it really mean? So now, let me first show you how to represent under-approximation in our approach. So each ASC node, which corresponds to a query operator, is assigned an under-approximation, represented as an array, possibly more than one dimension. And the query's under-approximation consists of the array for each ASC node of the query. And then for n queries, the under-approximation is described by a mapping M, which maps each ASC node of the queries to their under-approximation. So now, let me explain this in more detail. Let's start by understanding what the under-approximation actually means for a query operator first. Take the join operator from Q1 as an example, which corresponds to the ASC node named V2. So the under-approximation V2 is represented as a 2x2 matrix, where each element of the matrix is corresponding to a pair of tuples from the input tables. For instance, the top left element of the matrix corresponds to T1 from faculty and T3 from teachers. And each matrix element controls the join behavior of the pair of the tuples, which indicates whether the corresponding tuples satisfy the join condition or not. And each element of the matrix may take one of two possible values. If the value is T or true, it means the corresponding tuple pair satisfies the join condition and will be joined. Otherwise, if it is F or false, it indicates the tuple pair doesn't satisfy the join condition. So here, we have a concrete example of an under-approximation for this operator. And in this case, most pairs are marked F, while the value for the pair of T2 and T4 is T, meaning that in this under-approximation, it tracks the behavior where only the pair of T2 and T4 satisfy the join condition and will be preserved in the output. So essentially, this under-approximation represents one possible way that the join operator can behave, focusing on a smaller subset of all possible inputs. So this under-approximation for the operator can be encoded as an SMT formula, which encodes one particular input-output behavior specified by the under-approximation for this operator. Then, to encode the under-approximation for queries captured by M, we conjoin the encoding for each AST node in the queries. And as a result, the final formula also captures only a subset of query behaviors. And finally, we append the property that states the output of two queries should be different. And if the formula is satisfiable, the model will give us an input database that meets our application property. So now, we have seen how under-approximations enable us to track a subset of query behaviors efficiently. But what we have done so far is assuming a specific under-approximation for queries. So here's the question. What if the particular under-approximation misses the behavior we care about? So to address this, our second idea is to define a family of under-approximations that collectively cover all behavior of interest, and then perform search within the family, therefore making our approach complete. So in this way, if one under-approximation doesn't capture any behaviors that meet the application property, we search for other under-approximation within the family until we find a desired one, or the search space exhausted. So I will then explain how to define a family of under-approximation. So to build the family for queries, we need to first define a family of under-approximation for each operator first. So now let's use the inner join as an example. Recall that in the matrix for inner join, each element corresponds to a pair of tuples and can take either true or false. So every under-approximation in this family needs to assign a value to each of these matrix elements. So for example, if both input tables have 2 tuples, then the output table may contain up to 4 joint tuples. This results in 2 to the 4th, which is 16 possible under-approximations, covering all possible join behaviors of interest. And then to define the family for queries, we combine the family for each AST node of the queries compositionally. And in this way, each under-approximation in this family corresponds to a specific subset of query behaviors. And with the defined family of under-approximation for queries, we are able to systematically explore different under-approximations using search. And during the search, it is clearly too slow to enumerate each individual under-approximation one by one within the family. So in our technique, we use the so-called conflict-driven under-approximation search that learns the conflict from unsatisfiable under-approximation and avoids similar root cause in the future to accelerate the search. And due to time constraint, please refer to our paper for the details of this part, and I'm also happy to discuss it offline. And finally, we have evaluation. And to evaluate Polygon in real-world scenarios, we use over 30,000 benchmarks across 2 real-world tasks. And the first task is equivalence refutation, covering more than 24,000 query pairs from various sources. For example, one source is from LeetCode, where each benchmark is a pair of a user-submitted query accepted by LeetCode and a ground truth query. And the second task is query disambiguation, where the goal is to evenly split n queries into 2 clusters. And in our evaluation, we consider n is 50 and n is 100, giving us 2 sets of benchmarks, each containing either 50 or 100 queries per benchmark. And each benchmark is curated in a way that's guaranteed to be solvable. So we compared Polygon against a wide range of existing approaches. We included symbolic approaches that precisely encode the semantic SQL queries, and we also have fuzzing-based approaches that generate test inputs for SQL queries with considering no or very basic semantic information. And our evaluation shows several key points about Polygon's performance. For the equivalence checking task with a 1-minute timeout, Polygon can refute over 5,400 query pairs. That's about 1.7 times more than the best existing approaches. So given that most query pairs are actually expected to be equivalent, this is a surprisingly high number. And in terms of efficiency, Polygon can solve the benchmarks with a median solving time of only about 0.1 seconds. For the query disambiguation task with 100 queries per benchmark, Polygon solved about 97% of the benchmarks within 1 minute. And the median solving time was about 18 seconds, whereas the best baseline solved only about 68% of them. It's also worth noting that these benchmarks were highly complex, with a median of more than 400 ASC nodes per benchmark. So this highlights the capability of Polygon of solving very hard tasks efficiently. And that brings me to the end of my talk. Thank you for your attention, and I'm happy to take any questions now.
Okay, questions. I think we have someone going to run a mic around to where the questions are. Any brave souls want to kick us off? Or I can take a shot at it. I noticed in the way that you're using these matrices to represent different under-approximation strategies that it seems like there's probably a lot of symmetries there where there are different matrices that really represent the same idea. You can just like flip them around there, the diagonal or something, and it should be treated the same. Do you take advantage of those symmetries to speed up the symbolic operations that you perform?
Actually, I think I'm not sure if there's any symmetry because each element of the matrices or the array may correspond to different pairs of tuples from the input tables. So even though they are symmetric, they may be two different matrices. So
I was thinking of how it seems like for each of the tables that you're modeling, you should be able to permute it arbitrarily and not meaningfully change the satisfiability problem that you're looking at because there's no special identity of the elements in there. Is that not the case?
Can you explain how to like flip the tables?
So in general, we think of SQL tables as not even being ordered. So table with 1 and 2 as the values is the same as 2 and 1, but it looks like you're distinguishing those in the way you set this up.
Yeah, I see. Because we consider the operator like order by. So in that case, the ordering in the tables matters. So yeah.
Isn't the database engine allowed to reorder arbitrarily anyway? If you haven't asked for order by, you might get any order.
Yeah, because we use the list semantics, so we consider the ordering of the tuples in the table.
Okay,
yeah.
Thank you.
Yeah. Thank you.
We have a question over there. Get your steps in today.
Thank you. Yi Hong from University of Washington. So I wonder, what features of SQL you support? Is there any feature, any major feature you don't support in this project?
We currently don't support window functions like string operations, but we do support major features like drawing, order by, order by, auto drawing, the other common expression. Yeah.
I see. The other question I have is, it seems basically you decompose this problem into a series of under-approximations, and it seems like they can be solved in parallel. Have you tried running multiple solvers on different under-approximation?
No, we haven't tried that, but that could be an interesting direction to try in the future. Yeah.
Thank you.
Thank you.
Maybe we could get Yuepeng up here to plug in, and there's maybe enough time for one more question overlapping that operation. Where's Yuepeng?
I have a question about your matrix is mainly about projection and join. So what about other relational algebra operations, such as mapping from one to another? Yeah,
we have a different representation of the under-approximation for different operators. So for a filter, the under-approximation is represented as an one-dimensional array. And for drawings, the under-approximation is a matrix. And the meaning of the under-approximation for different operators are defined differently. So basically, we have different definition and different representation for different operators.
Okay, thank you.
Thank you so much.